everyone, I'm welcoming you all once again to this channel. So in today's session of Fortran programs, we will try to solve the numerical integration, and here mainly we will use the trapezoidal rule to solve the numerical integration. So let's start the video by solving the integration for sin x. So as we know that sin x is a very simple and common function in mathematics, and if we will integrate sin x over this limit, then we will get minus cosine x, and if we will apply the limiting value from lower to upper limit, then we can have the value of cos x at those limits. But here this is an indefinite integral, so here the c is nothing but the integral constant. And here what we want to do, so we want to integrate sin x, and here we have taken the variables as real data type, and those variables are a, b and the result. So a is the lower limit, b is the upper limit that we have defined, and in the result part what we have defined, like this is minus cos b plus cos a, this is the upper limit, minus of minus is plus, so cos a, and at the end we are printing the result. So this is very simple code. Here we have not taken any such function, rather we as we know that sin x integration is minus cos x, so simply we are putting the value of upper limit and lower limit in the place of cos x, and we are getting our result. Next, I can show you this sin x integration code over here. The same code we have written over here. So I am going to run this now. To give any certain value, suppose I am taking the lower limit as 4 and upper limit as 6, you can take any value. And here what we are getting, the integral of sin x from 4 to 6 is minus 1.61. okay, so now let's go again for our trapezoidal rule. So the next part for this video is the trapezoidal rule. So what can we do by using this trapezoidal rule? So here also, for any function f of x over a limit from a to b, which can be divided by too much sub interval, like n number of sub intervals, then with that division, how can we find out the limit, the integral of that function? That can be done by this trapezoidal rule. So here as we are having n number of sub intervals, then we can have different steps. So if we are going ahead from a to b, then for each of these n number, like for n number of intervals will be there, and after passing through each interval, one can start from a and can end at b. So this way this function will go from a to b, and we have to integrate the functional value, like we have to integrate mainly the area under the curve, and that can be done by this trapezoidal rule. So the integral is approximated as this: f of x dx, which is and the integration is limiting from a to b, is nothing but nearly equal to h by 2 f of a plus 2 summation over f of xi plus f of b, where axi is nothing but a plus ih, for I is equal to 1 to n minus 1, and here the h is the step size, that is from b minus a divided by n is the number of sub intervals. So if we will see this function, the function f of x is in blue color, so this is our main actual function, okay, and which can be approximated by a linear function. So the linear function is the red in color, so the area under this will represented by this integration. So the same thing we can also see from the Wikipedia of trapezoidal rule. So here you can check that the trapezoidal rule works by approximating the region under the curve of the function f of x as a trapezoid, and calculating its area, and it can be done by this formula. So this is the same formula as we have done, and after certain approximation, here is the final expression for the formula that I have shown there. So yeah, so this is the the final formula that we are using in our calculation. So this way you can check if you don't know what is trapezoidal rule. Mainly students in BTech or MSc, say BTech, MSc or BSc, in those level they require this kind of rules to do some numerical integration and all. So now let's go to our next part of implementing the same trapezoidal rule into our code. So here is a simple code to find the integration of sin x using the trapezoidal rule instead of our normal integral function. So here what we have taken, a, b and h, like h is the step size and here is integral is for the integral value, and n is our subinterval and x is the function. So let's start. So here we want to enter the lower limit, upper limit and the number of intervals. Then we have calculated the h as per the given formula, that b minus a by n, and the integral is 0.5 into f of a plus f of b. So similarly here you see that 0.5 is why 0.5, because this is 1 by 2 and f of a plus f of b. So this integral here we have taken, and we will also take this integral to further step inside a do loop. So now here we can check that we have started our do loop, and here the do loop variable is going from I to n minus 1, as we have seen here that this I is going from 1 to n minus 1. So similar way we are writing our code, and here the x will be nothing but a plus ih, as we have seen here x is nothing but a plus ih. Okay, and next we want to we want to do the looping over this integral. So integral is equal to integral plus f of x, as we know that this was the another summation which was inside this loop, and that's why we have taken a loop over here, that is from 1 to n minus 1, and we are summing all the integrals in together. Now this integral will be multiplied to h, so you can see that. So now our final expression is h by 2 f of a plus 2 into f of x, which is summed over I equal to 1 to n minus 1 plus f of b. So this way our integration is done. Next we want to print our result, and also here the function, like the main function of function for which we are doing the calculation, that we have not taken, so that we will take inside this function. So we have already seen our videos on functions, subroutine. So here we have this entire code contains a function, and that function is a real function f of x, and here the input variable is x and f is the sin x. Then here we are ending the function f, and we are ending the program trapezoidal rule. Next let's go and implement the same code. So here is the code to same code I have written over here also. So now let's run this, and here it is also asking for the lower limit and upper limit. I am giving the lower limit similar to the previous code, so 4 I am giving lower and 6 I am giving as upper limit, and here the number of n values. So let's start with a lower n value. Suppose I am giving the value as 2. So let's see what is happening. So now you see that the approximate integral is 1.47, where we have got 1 minus 1.61 when we did the simple, like the normal integration. That means this is not that much accurate. So what can we do? We can run this again, and we can increase the number of intervals to see what is happening. So I'm this time I'm entering 4. So now you see the value is increased from minus 1.4 to minus 1.58, and if I will further increase the n value, then what will happen? So I am entering 6 this time. So you check that this is now minus 1.59. Again by doing the same with little larger number, suppose I am giving 10. Okay, now you check that this integral is now minus 1.608, and which is almost similar, like very near to this minus 1.61. So here another rule is, as the number of intervals will increase, the approximation, like the value of this like the error will be minimized. There is also another formula to find out the error in trapezoidal rule, that you can find from here, that how to find the error during this trapezoidal rule calculation. It was somewhere here. Yeah, so here the asymptotic error is estimated for n tends to infinity is given by b minus a square divided by n square. If we will simply write, so what can we write, that our error is inversely proportional to n square. As our n will increase, so the error will also decrease. That means if this denominator will increase, this e value will decrease. That means so this is what we have seen here. As we are increasing our n values, our like our integral is coming towards the exact value. So this way you can try, and I hope you guys are understanding. So this much for today's session, and thank you all, and bye bye.